So we're going to talk about the equilibrium expression, and it is given a hypothetical reaction, A moles of A, compound A, B, and C, and D. And what people say all the time is KEQ, the equilibrium constant, is equal to products over reactants to the stoichiometric power. And what this means is I take my product concentrations, the concentration of C, and I take it to its stoichiometric coefficient in blue out here. That's the number of moles on each of these. So C to the Cth power times D to the Dth power divided by, those are the products, divided by the reactants, A to the 8th power and B to the Bth power, whatever we have. So that's the general idea. People memorize products over reactants. So we'll go through several different examples here. So example 1, let's look at N2O4 in equilibrium with 2NO2. And as you know, these are gases. And so if we write the equilibrium expression, now these are gases, so you might see different types of equilibrium. You can have KEQs with concentrations, and if it's in concentrations, it's called KC for concentration. Or you can have KEQ, and we can use units of pressure in atmospheres, and that will be called KP. You'll see these in the homework. Don't worry about it too much. If you see KP, use pressures. If you see KC, you use molarity. For N2O4 going to 2NO2 gases, the KP will be equal to the pressure of NO2, and we square it because there's a 2 out here in front, divided by, everything's multiply and divide, the pressure of N2O4, and it's to the first power, which you can put in, but nobody does because 30 to the first power is 30, etc. And that's the equilibrium expression for it. Okay, let's do a couple more. So I've written out a few reactions. We'll do this first one. You should be able to do it. Pause it and write out the equilibrium expression. In this case, KEQ is KP, so we write KP equal the products, pressure of NH3, and it's squared because of this 2 out here, divided by the pressure of N2 times the pressure of H2 cubed. And I'm getting that cubed from that number out here. There's a 1, of course, in front of the N2. So that's easy enough. Let's look at the next reaction. HF plus H2O gives us F minus plus H3O plus. This time we're going to use KC because they're solutions. They're not gases. And so our expression is going to be products over reactants, concentration of F minus to the first power times the concentration of H3O plus to the first power divided by the concentration of HF times the concentration of H2O. Now it turns out that any pure liquid or any pure solid, water is a pure liquid, is going to have a concentration of 1. I expect you to show this in there, and you can show it that it's 1. If you leave it out because it's 1, I might take a half point off or something like that. We'll see. So all the stoichiometric coefficients are 1, not shown here, and that's why there's 1s in all those. Let's do a slightly more complicated one. So again, this will be Kc because they're aqueous solutions. KEQ equal Kc. Okay, that's what the equilibrium constant is, a concentration 1, and so it'll be the concentration of vanadium plus 3 squared times the concentration of Sn plus 4 times the concentration of H2O squared divided by the concentration of H plus to the 4th power times the concentration of VO plus 2 squared times the concentration of 10 plus 2. And these terms here, the squared term from the vanadium comes from this 2 here. The squared term for the water comes from the coefficient in front of the water. H plus is this 4H plus up on the left. And VO plus 2 is on the left, the 2 in front of the VO plus 2. Okay? We also know that the concentration of water is 1. Okay, let's do the final one. A very complicated one, but it's really not that bad. KEQ is going to be a concentration because they're solutions. We know this because they say aqueous out here. And so we will get the concentration of VOOH2 to the 40th power times the concentration of HCO2 minus to the 15th power times concentration of OH minus to the 9th power times the concentration of K plus to the 24th power. I had to put the K plus down here below. Divided by the concentration of H2O to the 32nd power times the concentration of K3 V5O14 to the 8th power times the concentration of HOCH2 CHOH CH2OH to the 5th power. Now, we can make ones out of all our solids. Remember the 40th power comes from the 40 here, and the 15 comes from the 15 in front of the HCO2 minus, etc. So any pure solids, this is a solid up here, the vanadium, OH2, and so this goes to 1. The only other, I have a pure liquid, water is 1, and the K3V5O14 is 1. Okay, there you go.